Acid-Base Titrations. A titration is a very important laboratory procedure. In a titration, one solution is carefully added to another until the endpoint is reached. The two solutions contain the reactants in a chemical reaction, and the endpoint is when the two reactants are in the stoichiometric ratio, that is, the mole ratio shown by the coefficients in the balanced equation. How the endpoint is determined depends on what the reaction is and how we are performing it. For an acid-base titration, the base is usually added to the acid. There is no particular reason why this has to be the case or why we need to know the molarity of the solution we are adding, as long as we know the volume of each solution when we reach the endpoint and the concentration of one of the two solutions. The endpoint occurs when the moles of acid and the moles of base are in the stoichiometric relationship, which is usually 1:1. The endpoint can be determined by using a pH meter or by using an appropriate indicator. For the titration of a strong acid with a strong base, the most common indicator is phenolphthalein. Indicators are substances that change color with pH. Phenolphthalein is colorless in acid and a deep reddish pink in base. This change from no color to a color near the endpoint makes it easy to identify the endpoint, and is the main reason for the use of phenolphthalein and for the fact that we usually add a base to an acid. Titration of a strong acid with a strong base. If we look at the pH during the titration of a strong acid with a strong base, for example, 50 milliliters of 0.1 molar HCl with 0.1 molar NaOH, we find an interesting pattern develops. Let's look at 4 regions of the graph. At the beginning of the titration, only hydrogen ions and chloride ions are present in any significant amounts. The concentration of the H+ is 0.1 molar, so the pH is 1.0. As we begin the titration, the OH- reacts with the H+, gradually decreasing the concentration of H+. This continues until we get near the equivalence point. Just as a sidelight, when 90% of the H+ has reacted with the OH-, the concentration of H+ will be 0.01 molar, and the pH will be 2.0. That is, the pH will only change 1 unit while you do 90% of the titration to the endpoint. Just before the equivalence point, the pH starts to change rapidly. For example, going from 90% of the H+ reacted to 99% reacted, just another 9% towards the equivalence point, causes the pH to rise to 3.0, another whole unit. In this region, only the cation from the base, Na+ in this case, and the anion from the acid, Cl- in this case, are present in significant amounts. At the equivalence point, where the moles of acid equals the moles of base, we have essentially a water solution of the salt made from the acid and the base, in this case NaCl. Because we have a strong acid and a strong base, the pH at the equivalence point is 7.0. Right around the equivalence point, the pH may change as much as 6 units with as little as a couple of drops of base added. Once we are past the zone of rapid pH change near the equivalence point, as we continue to add base, the pH continues to slowly rise as the concentration of OH- increases. In this region, we have significant amounts of Na+, Cl-, and OH-. When we look at the titration of a weak acid and a strong base, at first glance the graphs look similar, but not identical. Let's look at the same 4 regions of the graph for the titration of 0.1 molar acetic acid, HC2H3O2, with 0.1 molar sodium hydroxide. At the beginning, because we have a weak acid, the acid is mostly undissociated, so we have mainly acetic acid, with a little bit of acetate ion and H+ present. When we begin to add the base, that produces the conjugate base. The presence of the conjugate base has a significant impact on the pH of the system, since this makes a buffer solution. This region, from shortly after the start of the titration to shortly before the equivalence point, is often called the buffer region because it is in that region that we have a buffer solution. Again, near the equivalence point, we have a rapid change in pH, though it is not as large as the change for a strong acid, strong base titration. Because we are titrating a strong base with a weak acid, the pH at the equivalence point will be higher than 7. This makes phenolphthalein the indicator of choice for these titrations. At the equivalence point, we again essentially have a water solution of the salt of the weak acid, in this case sodium acetate. The acetate ion hydrolyzes to make a basic solution. After the equivalence point, we again have a situation where the pH slowly rises. In this region, we no longer have any significant amount of the weak acid, so the solution is made up of Na+, OH-, and acetate ion, C2H3O2- in water. As we have already seen, in the buffer region, we need to use a two-tier approach to be able to determine the pH of the solution at any point. This graph shows what the pH graph would look like for weak acid with Ka's of different values. Note that the weaker the acid, the higher the initial pH is, and the shorter the section where the pH changes rapidly. Titration of a weak base with a strong acid. If we add a solution of a strong acid to a solution of a strong base, we get the red line, which is essentially the graph for a strong base added to a strong acid flipped around. When we add a strong acid to a weak base, we start at a high pH, create a buffer range before the equivalence point, and reach the equivalence point at a pH below 7. The indicator of choice for this type of titration is methyl red. Titrations of polyprotic acids. When we have a polyprotic acid, we have an equivalence point for each of the dissociations of the acid. For H3PO3, there are 2 acidic protons, so we have 2 rapid increases in pH. Each is shorter than for a monoprotic acid. The calculations are more complicated, particularly at the equivalence points. We will not get into this type of calculation in AP Chemistry.